Hello and welcome to this, the 8th event in a week of lectures and webinars to mark the 40th anniversary of the IGS. In this week, we are showcasing great thinking and insights from IGS members around the world, and also giving you the opportunity to quiz the IGS officers on the activities of the IGS and our future plans. So this is Chung-Sik Kyu, the IGS immediate past president. I hope you remember. Please note, today's event will be recorded so that we can share it with members who are unable to make it to the live session. So it is my great pleasure today to introduce Professor Fumio Tatsuoka. I don't think we really need to introduce him, but I'd like to go over his brief CV. Okay. Professor Tatsuoka is a professor emeritus of the University of Tokyo and Tokyo University of Science. He has previously served as the vice president of ISSNGE, president of the Japanese Geotechnical Society, and vice president of the Japanese Society of Civil Engineers, and president of the International Geosynthetic Society. Professor Tatsuoka specialized in the deformation and strength characteristics of geomaterials, ground improvement, and geosynthetic-reinforced soil structures. He has received numerous awards, including the IGS Award, the Mercer Lectureship, and multiple Hogan Togla Awards from ASTM, multiple Best Paper Awards from Geosynthetics International Journal, and geotextiles and geomembranes, and also the Bishop Lectureship of ISSMGE, and most recently in 2022, the Kevin Nash Gold Medal from ISSMGE. So today, Professor Tatsuoka is going to present on the impact of Japanese innovation on the development of geosynthetics and show how geosynthetics reinforced soil structures with unique features were developed in Japan. So if you have any questions and comments, please use the Q&A function, and I will ask them of Professor Tatsuoka at the end of the presentation. So with that, Professor Tatsuoka, welcome, and over to you.
Okay, thank you very much. So I show my slides. Okay. Okay. The topic is the synthetic reinforced soil structure in Japan, many requirements and the solution. Okay, winter, hold on. Okay, in the abstract, in parallel with the development of IGS for the last 40 years, in Japan, the synthetic reinforced soil structures having unique features were developed, responding to many requirements. The requirements are basically high performance and high cost effectiveness. Specifically, first is the no pile foundation, but high stability and small radial deformation. Second is the narrow space occupied during and after construction. Third is the facing supporting other structures, for example, bridge abutment. Fourth is the cost-effective, stable retaining walls on slope. Fifth is the high stability against seismic load, scarring, erosion, and tsunami. And sixth is a reliable structure for high-speed railways. As a solution for DRS retaining walls, after the deformation of the grid reinforced backfill and subsoil caused by the construction of the reinforced backfill has taken place sufficiently, full height rigid facing is constructed by casting in place fresh concrete directly on the grid wrapped around wall face in such that the fluoride facing is firmly connected to all the grid layers. Early 1990s, GRS bridge abutment was developed. One end of a simple girder is supported by a fixed bearing arranged at the top of fluoride facing of a GRS wall, or both ends of a simple girder are supported by fixed and movable bearings at the top of fluoride facing of a pair of GRS retain walls. In total, 185 have been constructed. Then GR's integral bridge was developed. Both ends of the continuous girder are structurally integrated to the top of the fluoride facing of a pair of GRS retain walls at the last stage of construction. 14 have been constructed. In the meantime, a number of embankments and conventional type retain walls, bridge that collapsed by severe seismic load, scarring, erosion, or tsunami, were reconstructed to these GR structures. After 40 years, the total wall length exceeded 200 kilometers. Many GR structures were constructed for high-speed railways. All of them have been performing very well with no problematic case during and after construction, while very high cost effectiveness with low maintenance costs has been validated. So this is showing various types of mechanical stabilized earth retain wall having different types of facing and reinforcement. This is 40 years ago, stationed 40 years ago. So facing is either flexible, not developing high earth pressure on the facing, or stiff, developing high earth pressure on the facing. And reinforcement is either inextensible, such as metal strip, or extensible, typically polymetric planar zero grid. This combination is this TRMA, a metallic screen facing. This change moved to a discrete panel facing like this. Then with zero grid, we constructed a wrap around facing like this. However, the wall face is too deformable and not durable and aesthetically not acceptable. So we moved to this modular block facing. This is a substantial improvement. Yet, further developments were necessary to respond to many requirements and requests. We have to go to the next step. So this is a number of problems with conventional type retain walls, basically low performance and low cost effectiveness. Specifically, the first is the need for a costly pile foundation to ensure sufficient stability. So this is because the conventional retain walls are cantilever structure. So we have a large forces in the facing requiring a massive and strong facing. And we have a large overturning moment and large lateral thrust load at the facing base. This results in unstable behavior, particularly by severe seismic loads and large stresses concentration at the facing base. So usually we need a costly pile foundation. So this is one example in Japan. This is a very soft clay, very thick, so we need a retain wall. When we construct a cantilever retain wall, we need a very long pile, but this is utterly not cost effective. Second problem is that we may have a too large post-construction deformation settlement. So we have many problems with conventional type bridge abutment. One problem is the bump here by settlement by continuous. This may take place continuously by traffic loads for a long period or suddenly by a seismic load. This is a bump by a seismic load. You can see there's a settlement in the backfill. We have numerous similar cases. This is another case during 1995 January 15 Kobe earthquake. So railway here and here, and you can see a settlement here, creating a bump. Furthermore, Japan is congested and narrow with frequent severe natural disasters and a strong need for a renewal of many old soil structures. So the following problems should also be solved. Third one is a narrow space available during and after construction. This is one case of construction of cantilever type retaining RC cantilever retaining wall. We need a propping here, so a wide space is occupied in front of the wall for our propping supporting external concrete form. Well, this is a GRS approach field with wall faces on both sides. So this is under construction. The problem is how to construct facing here and here in very narrow space available in front of the wall face. Fourth is a cost-ineffective construction of the facing supporting other structures, including many problems with bridge abutment. So here, this is showing conventional retaining walls and RC viaduct. Advantage is that limited occupied space and the ability to support other structures. But disadvantage is not cost effective. In comparison, GRS retaining wall with facing of modular blocks or disc panel, this needs a lower construction cost. But unlike conventional retaining walls and RC viaduct, the facing is not deep enough. So a buffer zone here is required for safe operation of road and railway, so the occupied space becomes wide. And a facing cannot effectively support other structures, so some foundation become necessary. So this is showing a number of serious problems with conventional type bridge abutment. First, we construct many piles, then massive earth abutment, then we construct the backfill, then earth pressure and settlement and lateral flow of the subsoil by the construction of massive backfill. We may have a negative friction or bending moment of the piles. And we place bearings, fixed or movable. This is costly and for construction and also for long-term maintenance. Then we place a simple girder. Then we have a long-term settlement. And in general, we can say low performance and cost ineffective. And fifth problem is cost ineffective construction of stable retaining wall on slope. So we need a vertical wall here, in this case, to widen the crest of the embankment without occupying the space in front of the embankment. However, by a conventional cantilever retaining wall, we need a large excavation here, and we need a use of a temporary anchored seat pile. This will result in an increase in the construction cost and period. When we construct the MSC retaining wall having a facing of discrete panel or modular block, this is more effective, cost effective, but their grid length to a wall height is usually larger than 0.7, 70% for sufficient wall stable. Then we may need a large excavation. So we have a number of similar cases. 6 is a low stability against severe seismic load, scarring and erosion and tsunami. So this is a number of problems with seismic loads with conventional type bridge abutment, movement of the pile, abutment, and the dislodging of girder and settlement. So this is one case of the collapse of wing wall for approach here. Here's the bridge abutment during 1995 Kobe earthquake. And this is the collapse of RC retain wall. Here is bending during 1995 Kobe earthquake. And this collapse of masonry retain wall by the 1995 Kobe earthquake. You see full collapse. And this is overturning failure of a gravity type retain wall, also during 1990 Kobe earthquake. Yeah. So this is the collapse of another type of gravity type retain wall. So like this. So overturning failure took place despite a seismic design was performed using a KH.2 with an allowable lower limit of safety factor equals 1.5. This means conventional seismic design is not sufficient. Also, we need a more stable wall. This is a failure of road and railway during 1994 earthquake. So this is a cross-section, blue line is a cross-section before the collapse. And this, here is the gravity retain wall and slope, and this black line is after failure. This is a failure at another site during the same earthquake. We had a couple of similar failure during this earthquake. And here is the collapse of the gravity type retain wall here, moved to from here to here. This is for a road and residential area. So we have this damage to houses. And this retain wall original place here moved to here. So this move the view from the back, and this cross section. So this is showing a railway in the mountain area, and broken lines are tunnel, and the red arrow means the embankments for railway. This collapsed by floods in 1990, like this. Here's a tunnel, and the embankment totally disappeared. A small diameter drain pipe was crossing the embankment. This was cracked by flowing timbers. Then a natural reservoir was formed. Then embankments was fully eroded by overtopping flood. And here's a view of this tunnel exit on the right side and left side. So this is another case, collapse of a masonry wing retain wall or RC bridge abutment by scarring in the subsoil and the erosion of the backfill. This is cross view, like this. So approach field totally disappeared. And this is the collapse of a railway embankment by scarring at the embankment, two of the embankment. So we have, this is a conventional type cantilever retain wall. We often observe overturning failure by scarring below the wall. This quickly followed by a global collapse of embankment. This results in the closing of roads and railways. This is a typical case, collapse of a gravity-type sea wall for length of 1.5 kilometers by ocean waves during a storm, 2007, close to Tokyo. In front of the wall, about 1 meter wide sand beach here disappeared due to erosion by coastal current during the last 60 years since the completion of this road. which result in a frequent direct attack of storm ocean waves to the wall. This is the station and RC viaduct. And before the 2001 Great East Japan earthquake. This is after the earthquake. You can see a collapse of RC viaduct by tsunami. Tsunami was 8 to 9 meters higher than the railway track elevation. This was elevated 14 meters above the sea level. So this is during the same earthquake, here in the Pacific Ocean, two simple girders have been washed away toward inland by a great tsunami from the Pacific Ocean. So as a result, these structures are not reliable for high-speed railways. So for the last 40 years, continuous efforts were made to develop the DRS structure that can alleviate these problems. The solution is by the three technical breakthroughs. First is the use of full height ridge facing for changes from a low earth pressure to high earth pressure on the facing, and from the facing as a secondary non-structure component to the facing as a primary structure component. Second is the structural integration of the facing, full height facing to the reinforced backfill, and the girder to a full height ridge facing with GRS internal bridge. For a change from a statically determinate but unstable structure to a statically indeterminate but stable structure. Third is stage construction like this. For a change of construction sequence from the facing before the backfill to the facing after the backfill. So then we reach to the this full height ridge facing after 40 years. So why this solution is relevant? Some reasons. So I will explain this for two terms. So GRS retain wall is not cantilever structure. So force equilibrium A along the potential active zone plane is important. At each level, active earth pressure is resisted by the tensile reinforcement. This is unlike cantilever structure. Therefore, a small overturning moment and a small lateral thrust load. So usually a costly pile foundation is not required. However, when the facing is flexible, we have a very low earth pressure on the facing, which results into a low tensile forces in the reinforcement, in particular at low level. In the active zone, we have low confined pressure, therefore low strength and stiffness of the backfill, so large wall deformation, low stability of the wall. On the other hand, when facing is firmly connected to reinforcement, we have a high earth pressure on the facing, which results in a high tensile forces in the reinforcement, even at low levels. Then in active zone, high confined pressure and therefore high strength and stiffness of backfill. So we have a small wall deformation and high stability of the wall, even immediately back of the facing. Right? So full height facing for DR retaining wall is actually a continuous beam supported by many reinforcement layers at a small span, usually 30 centimeters. The behavior becomes unlike cantilever structure. There is a small force in the facing and a small overturning moment and small lateral thrust load at the facing base. So a pile foundation is not required and the wall becomes stable even against severe seismic loads. So third point is the stage construction. So this is showing that before the construction of the reconstruction of the slope face. This is the complete GRS wall, but before the construction of flow-hydrated facing. And this is completely GRS facing after construction of flow-hydrated facing. This is the typical case. So stage construction first is the start of construction. Here the leveling part and embedded part of flow-hydrated facing and placing gabions, gravel backs wrap around with the grid and compaction of the first layer. And for a good compaction of the backfill is achieved by a small lift, 15 centimeter, ensured by a small vertical spacing, 30 centimeter, and no rigid facing existing during compaction. Besides, a small vertical facing, 30 centimeter, results in a large contact area between the grid and backfill, and then high stability of the reinforced backfill as a composite. Then this is the completed GRS wall here, but this is before construction of flow-hydrated facing. Then, after compression of the backfill and subsoil has taken place sufficiently, flow-hydrated facing constructed by casting in place fresh concrete here directly on the grid around wall face. So fresh concrete entered a gravel-filled box here through aperture of the wrapping the grid. As a result, flow-hydrated facing is firmly connected to the grid layers. To confirm the connection strength, we perform a number of tests. This is a full-scale test. Here the test specimen cut out from the 40 centimeter full-scale flow-hydrated facing. This hung up under 1G, so no separation here. And this is the laboratory separation test. This is after separation test. This is a typical result, separation stress and separation displacement. The peak strength is much larger than the inertial load of 2 meter thick facing subject to horizontal acceleration of 1G. So the property required for the grid is first is sufficient strength and stiffness with low cliff deformation, and limited damage during backfill compaction, and high anchorage strength in concrete and backfill, and good adhesiveness with concrete. And fourth is a high long-term resistance against high pH of concrete. Third and fourth are particularly important as the grid is in direct contact with fresh concrete like this. So last stage is this is a completed wall. And this is a view of the same wall after 15 years. So this is a cross-section of the wall. So the advantage of stage construction is summarized here. First is the temporary facing consisting of soil backs or the alternative enhances effective soil compaction near the wall face. The temporal facing is strong enough for sufficient stability of the temporary wall here, while the deformable enough to accommodate deformation of the backfill and some soil. And during long-term service, the full-height rigid facing is stiff and strong enough to keep small the wall deformation, ensuring a high wall stability even when subject to severe earthing loads. And here, essentially no damage to the facing and the grid connection during long-term service and against severe earthing loads, because the post-construction differential settlement between the flow-height rigid facing and backfill is essentially zero, and the gravel backs protect the facing the grid connection. The last point is the potential deformation of the backfill and subsoil has taken place before the construction of full height rigid facing. So pile foundation to restrain the displacement of the facing becomes unnecessary. So when we use this GR retaining wall at the bridge abutment, the residual displacement of the bridge girder supported by GR bridge abutment is kept very small despite no use of pile foundation. This point I will explain later in detail. So, so now this is an advantageous feature of GR structure having stage construction full height ridge facing that alleviate many problems. For higher performance and higher cost effectiveness, by first is high stability despite no use of pile foundation, and very small post-construction deformation settlement. In this case, when we for the conventional cantilever retaining wall, we need long piles. But this problem is overcome by stage construction of GR-less retaining wall without facing first, then preloading and settlement about 1 meter, and removal of preload, then construction of full height is facing. So this is during preloading. Settlement is about 1 meter, and construction of full height is the later after removing the preload. So full height rigid facing is free from large backfill settlement and irregular wall face deformation. This is this wall after 20 years. So third point is narrow space occupied during and after construction. This, when we construct conventional type RC cantilever retaining wall, we need this space. But for the construction of GR retaining wall, here the full height facing under construction. So this is concrete form here is supported from inside of the backfill. So we don't use this space. This case, here is a GR's embankment, and we need a facing here. This place here, and no facing during construction, but facing is constructed in this space. Also in this space, construction GR full height ridge facing are constructed like this, because we don't need a space in front of the wall to construct full height ridge facing. And this issue, and GR's retaining wall with full height facing here, this is cost effective. This is largely by keeping the two advantageous features, 1 or 2 here, limited occupied space and ability to support other structures. So here the railway or road can be arranged very close to the wall face, so the occupied space is narrow, and full height rigid facing can effectively support other structures like this, despite no pile foundation. This is the case, is the full height rigid facing is supporting this electric supply structure, and the railway track is placed very close to facing. And fourth point is cost-effective construction of stable retaining wall on slope. When we construct conventional cantilever, here the problems of large excavation and anchored sheet pile. Same with this type of GR structure. Our case, GR retaining wall full height ridge facing, we use a short basic grid layers and to reduce slope excavation and not use anchored sheet piles. So a reduction in the wall stability by the use of short basic grid layers is covered by, first is a closely spaced planar grid layers having a high pull-out strength here. The second is several long grid layers and the use of full height ridge facing. These can cover the reduction of safety factor by making the grid short. This is a typical case in Tokyo. You can see excavation of the slope is very limited. So this is showing the zero grid arrangement by the current design. The length here, L basic, is the largest value among the 35% all height and 1.5 meter, and the length for residual wall deformation to be lower than allowable limit. In this case, the 2.5 meter is determined by this case 3 by analysis. This analysis is by this residual wall deformation is valued by overturning and lateral sliding, evaluated by Newmark method based on two-weight stability analysis, plus value of a shear deformation or equivalent reinforced zone with a width equivalent to the average length of the grid. So two-weight stability analysis, and A and B could be any place. The angle theta A, theta B could be any angle, and we seek the smallest factor. When by using full height ridge facing, and this point A become here, this makes for very stable. So the high full height ridge facing can directly support other structures. So full height ridge facing and closely spaced short base grid layers, together with several long layers, behave monolithically as a composite, not developing internal local failure. So we can expect high wall stability against overturning and lateral sliding and small shear deformation when subject to static and seismic earth pressure from the backfill and the external loads like this. Then we can use GIS bridge abutment as a bridge, retaining wall as a bridge abutment. So we have a number of programs. We may have a damage. The solution is this. GRS bridge abutment, this is a good solution. So we first construct the GIS wall, flat facing, and the girder foundation. This is stable because this is integrated to the flat facing, the bearing girder. So despite the no use of power foundation, we can expect very stable behavior even against severe such loads, and no bump here by the settlement by backfill, because the construction of full height ridge facing is after potential deformation of backfill and subsoil has taken place. The second is enhancement of good compaction of backfill, and third is firm connection of facing to all the layers. So this is statically determined due to the use of movable and fixed bearings. So the internal forces in girder and flat facing are not sensitive to the thermal and deformation of the girder and the post-construction deformation of the backfill and subsoil. So design of the girder and height ridge facing is not sophisticated. This is a typical case, start of construction and construction of GRS retaining wall and construction of the full height ridge facing and completed one. So, and this is the first GRS bridge abutment 2003, and the highest GRS bridge abutment construct 2012. By 2022, in total, 185, including those for high-speed railways, were constructed. So this is a pair of GRS bridge abutments supporting a simple girder by a movable and fixed bearings. This is a very good performance. So this is a typical case. Okay. あ、これか。これ。はい。Yeah. So this is good, but two remaining problems. One, the costly construction or maintenance of the bearings and the low seismic stability of the girder of the mover bearing. Then solution is GRS internal bridge. GRS internal bridge constructed in this way. Finally, here, structure integration. So we performed to evaluate the performance, we performed a number of static and dynamic model tests in the laboratory, and the full-scale model were constructed. This is a full-scale model, 14 meter, 15 meter in length. The span 5 meter, about 5 meter in height. We performed the lateral cycle loading test to simulate seismic loads and thermal effects. We constructed a number of GRS internal bridges. First one is here. Here the only span is 12 meter, but this is the first one. You can see slender girder and slender flood facing. This is because all these are structurally integrated to the reinforced backfill. Here are the 3 GR integral bridges here. The simple girder was washed away by tsunami during 2001 Great East Japan earthquake. So 3 candidates for restoration. One is a 2-span simple girder supported by the 2 pair of bearings, the same as the collapsed one. The second one, the single continuous girder, but by using a pair of bearings here and here. Third one is a GRS internal bridge without using bearings. This is continuous girder supported vertically at the center. So we compare the construction costs and seismic stability and anti-tsunami stability and maintenance cost. In all terms, the GRS internal bridge is the best. So this was adopted because of the best performance and the best cost effectiveness. This is during construction of GRS internal bridge. The total span length is 40 meter, and this is a completed one. Another place, the simple girder was away by tsunami like this. So here is a total span is a 60 meter. This is during construction, also like this. And this is a completed one. So 6 is a high stability against severe seismic load and scarring and erosion tsunami. So this is a GRS retaining wall, 1992. So this is the same retaining wall, 1995, a week after 1995 earthquake. So the wall survived. This is a view of the wall from the other side, you see. And here the collapse of the wall, this was restored to GRS retaining wall like this. This collapse, the mason retaining wall was restored to GRS wall like this. And this place is collapsed in this way. And this was restored to GRS retaining wall. Blue one is before the collapse. Black line is after collapse, and red one is after completion. This is the first train, and this during construction. Total wall height is 13.18 meter. This is another place. Here, restored to GRS retaining wall. Here is a collapse by conventional type cantilever retaining wall by scarring, but GR retaining wall with fluoride rigid facing is much better performance we can expect, because overturning failure of the fluoride rigid facing by scouring is difficult to take place. So embankment can survive, allowing emergency use of road and railway. So this one collapsed by like this, and this is restored to GR's retaining wall. And this is during the restoration. And I took this picture two weeks ago. And this have survived frequent attacks of storm ocean wave, on average twice a year. So this place was restored like this. Only 10 days required until the open of the service. This is much shorter than the period to construct a conventional cantilever RC retain wall. The fluoride rigid facing was constructed after the open of the service. So this place, embankment disappeared, but this was restored to GR structure, retaining wall, and reinforced slope. This is during reconstruction. This is a complete wall. So this place was reconstructed to GR structure like this, 5-meter wall, and zero-grid reinforced slope. And this place was fluoride rigid facing. So this place was restored to GR's embankment. Cross-section is this, the concrete facing is connected to GR grid layers. So finally, GR structure for high-speed railways. So this is a network of Japanese high-speed railway, and white and black stripe are in operation. Red one is under construction. So here, Hokkaido open to 1.201. This one site. R is a GR retaining wall. A is a GR split apartment. And I is a GR integral bridge, not here. B is a GR box culvert. And T is a GR tunnel entrance exit. Here, T. So all the GR structure were constructed in place of conventional type structures. So this is a cross view. This is a GR retaining wall with the fluoride rigid facing. This is GR box culvert. This is GR bridge apartment. This is GR tunnel entrance exit protection. And GR bridge apartment is constructed in this way. Here's a completed one. Yeah, this Kyushu opened last year. So GR retaining wall at the depot. And in this route of high-speed railway, among 88 bridge apartments constructed at the tunnel exit, 78 are GR bridge apartments. Here is a GR bridge apartment here, here, here. This is a cross view of such a case. Here's the GR bridge apartment. This is another GR bridge apartment. This is another case. Oh, here, this is GR bridge apartment. So GR integral bridge was constructed in this way, excavation of the subsoil. the construction of approach field. So geogrid reinforced well compacted lightly cement mixed gravel soil here. This is unreinforced backfill. Then the construction of fluoride ridge facing after deformation of the backfill and subsoil has taken place sufficiently. Then fluoride ridge facing is firmly connected to the grid layers. Then the arrangement of PC girders in this case, this is shown the displacement. Finally, the structural integration of both ends of the girder to the fluoride ridge facing, then construction of slab and others to complete the bridge. This is complete GS intern bridge here, and this is continuous RC slab track. This is a GS wing retaining wall, so inside is the backfill. This is showing the history of GR structures. Every year, this length has been constructed, in total 206 kilometers. And during this period, here the restart of construction of new bullet train, high-speed railway, and we have a number of earthquakes here. So we have learned a lot of lessons. This is showing the location of completed GRS retaining wall with fluoride ridge facing, GRS bridge abutment, and GRS intern bridge. Total completed wall length is 206 kilometers. Total number of sites is 1,424. So far, we had no problematic case during and after construction of in all these projects. So conclusion. So we showed a number of problems with conventional type retaining walls here from 1 to 6, 7, I explained. So the solution was by 3 technical breakthroughs. One is the use of fluoride ridge facing for changed from a low earth pressure to a high earth pressure on the facing, and from facing as a secondary non-structural component to facing as a primary structure component. Second, the structure integration of the fluoride ridge facing to reinforcement backfill and the girder to fluoride ridge facing with the intern bridge for a change from a statically determinate but unstable structure to statically indeterminate but stable one. The last is a stage construction or change of construction sequence from facing before the backfill to the facing after the backfill. So a number of GRS bridge retaining walls with fluoride ridge facing, GRS bridge abutments, GRS intern bridge, etc., have been constructed as an important permanent structure for total wall length more than 206 kilometers, many of them for high-speed railways. This accomplishment is due to high cost performance by high performance during long-term service and against severe seismic load, heavy rainfall, strong flood, and tsunami, and low cost for construction and long-term maintenance. The GRS bridge abutment is often used to support one end of a simple girder on a fixed bearing arranged at the top of fluoride ridge facing of a GRS retaining wall. This is much more cost-effective and much more stable than conventional type bridge abutment. In total, 185 have been constructed. All have been performed satisfactorily with essentially zero bump. This is now one of the standard bridge abutment structure for railway in Japan. GRS intern bridge consists of a continuous girder of which the both ends are structurally integrated to the crest of the fluoride ridge facing of a pair of GRS retaining wall, not using girder bearings. This is much more cost-effective and much more stable than conventional simple girder bridge In total, 14 have been constructed. GS bridge, integral bridge is now one of the standard bridge structures for rail in Japan. The last is that many of the conventional type embankments, retaining wall and bridge that collapse by recent severe seismic load, heavy rainfall, strong flood, high ocean storm waves, tsunami, etc., were restored to GR structures having flood facing like this. So thank you very much for your kind attention. And I acknowledge many my colleagues so far. Thank you very much for your kind attention.
Thank you, Professor Tatsuoka. Your lecture is always crystal clear and very informative. Thank you very much. Well, we have currently 3 questions.
Three questions.
I think 3 questions. So I'm going to share. I summarize the questions. So let me just try to share the
I'm
screen.
reading a question.
Yeah, let me see. Oops. So at the bottom, there is a Q&A tab. You can see the questions, right?
Yes, I can answer to, is there any special requirement for foundation of facing? No. Ordinary one is okay, not special.
Mhm.
So for clay is a difficult soil. So for backfill material, is it possible to use clay? Possible, but must be very careful. So good compaction is a must, and we have to wait some time until the deformation has taken place before constructing flood ridge facing. So many careful requirements. So the next is the GS abutment design section. Sometimes we see that embankment length of the upper is longer. But sometimes I need some long time to explain. Okay, for ordinary retaining wall, the short reinforcement at the bottom, long base reinforcement at the top, because the road and train are in parallel facing. So no problem of bump at the bottom and back end of the reinforcement. But bridge abutment, train or road is running in normal to the wall face. That means the largest problem is a bump at the end of the reinforcement. So the thickness of unreinforced backfill should increase from 0 to continuously to larger one. We have to avoid this continuous thickness. And also the bridge abutment, the very large lateral force by the seismic inertia force of Garda is applied top of the facing, right? It's a very big force. Then the facing and reinforced zone must be very stable against overturning. So for overturning failure, to avoid to increase the resistance, the bottom reinforcement is better to be long. So then, but depending on the ground conditions, several different arrangement we are adopting. But in any case, final stability is examined by stability analysis. So this is some kind of art to determine the arrangement. Mm-hmm. I need some more longer time. So maybe personally I can answer.
Yeah, I think your explanation was clear. I think Well, for the second one, which is about the backfill, I think if we can avoid clay, I think we should avoid the clay as a backfill. I think Tatsuoka, Professor Tatsuoka and I had discussion many times, but backfill is the most very important, as important as geosynthetics and geosynthetic, reinforced soil structure. So, the clay is very difficult the soil and gives a lot, also many big problems. So if we can avoid using clay, I think we have to do it. Professor Tatsuoka, you agree, right?
Yes, yes. But some backfill with fines, some limited amount of fines is okay. If we can do a good compaction, a good drainage.
Right. Okay, Professor Tatsuoka.
So more answer to this one, or many
there are actually many. Oh, okay. So let's
can I, what shall I do? Quickly I answer? Quickly.
Yeah, please. Yeah, I think it's
calculation, design, this is a computer program we are using. So limited equilibrium and response analysis. Next is they want to cast in place concrete cause damage to the plastic. No. So geogrid must have a high resistance against a high pH because of direct contact with concrete. And is it possible to share with the PD? Oh, okay. Okay. The research and design to spread fire. No. We didn't do a special research on this part because we don't use piles, and the full height ridge facing is constructed after deformation of the backfill. So no big actual load is applied. But with bridge abutment, some analysis we need for bearing capacity of the bottom of the face. Okay. Okay. Yeah, many studies we are doing for specification. Okay. Maybe over. I need some long time to answer in detail all these questions.
Yes, we wish we have more time, but if those who have questions, you can contact me so that I can relay your questions to Professor Tatsuoka, or you can directly ask, send your email to Professor Tatsuoka, whatever you want to do it. I think your question is quite important. So, again, thank you very much, Professor Tatsuoka. And even though you slightly away from the IGS activities, but we always admire your work and we try to follow your footsteps. Thank you very much. Okay.
Thank you very much for your kind words. Thank you.
Thank you very much. Well, right after this, we will have a session, which is as the officer session, starting right immediately after this. So stay tuned. Please don't go away. Okay, so I will take your questions related to the IGS strategic goal, which is trusted. So it's going to be probably 30 minutes. So I will explain to you what it is, and you can ask me any questions about this. Okay, so I will pass this on to Amir. Are you here? Okay, good.